Hsin-Ruey, also call me Ray from National JND University, and this work is cooperated with Professor Bingyu Chen, my PI when I was a postdoc researcher in National Taiwan University. And we propose ElastImpact, 2.5D instant impact on HMD. So impact is a common effect in VR, and there are many methods have been proposed to provide such feedback on users' body or limbs or even head to enhance VR realism. And even in some sci-fi movies, it envisions the future haptic suit to provide such impact as being hit in VR. Well, certainly this kind of feedback is what we're going to provide. Okay, so for the previous impact methods, impactor combines a solenoid and EMS to provide both tactile and force feedback for impact. And JETO uses an air compressor to emit a jet of airflow and to render the impact on a smartwatch. And in our previous work, Elastic VR, it extends an ES band using a motor and resists a brake to produce instant impact. And in fact, all these three methods have indeed provide impact, but only in specific directions, and none of them provide impact on their head or HMD. So for the works using the haptic feedback on HMD, gyro VR using the gyro effect to provide inertia resistive force when users rotate their head. And handover uses balloons to produce a hand reflex phenomena, which makes users to turn their head when being punched. And face push uses two motors to make the HMD push on user's face as being punched. And although some of this method proposed to render the feedback as being punched, but the feedback they provide are not real impact. So how impact on the head affecting user is still unexplored, especially in the multi-level and multi-dimensional. So to achieve this, there are some design considerations we should take account. And the first one is feedback realism. So the realistic feedback is required to enhance VR realism. So since the impact occurs instantly, and using hand reflex or pushing the face with gradual force increase are not realistic, or we say not exciting enough to users. The second one is mobility. Since we hope to allow users to freely explore and move in the VR scenes, so mobility is essential. Therefore, for the method with some bulky devices, such as an air compressor, are improper. The third one is safety and comfort. So for intense feedback like impact, the safety and comfort are the premises. Therefore, for impact level and the methods with potential risks such as using EMS on the head should be considered. So we want to achieve this although users are being punched, but they are still safe or even feel comfortable, and they can do this for all day. Okay, so based on this consideration, we choose and improve the design of the concept of Elastic VR and to build a smaller, lighter, but more powerful impactor in ElastImpact. So there is an elastic band and with a wire nut and a wire in an impactor. And it's blocked by a mechanical brake consisting of a chanion and mortise controlled by a servo motor. And a DC motor with a rotary encoder and a winding axle extends is in different distances to store the impact power. So when the brake releases, the impact is produced and delivered via the wire. So to achieve 2.5D impact on HMD, we combine the normal impact in ZSX and also the tangential impact on the XY plane. So for normal impact, two side impactors are attached on the tube strap of the HMD and via the vocal fasteners for different head sizes. And for the normal impact, and therefore when impact force is produced, HMD is instantly push user's face and in normal direction to provide 0.5D normal impact in the axis. And for tangential impact, the rotatable impactor is in front of the HMD and is connected with a barrel. So this is how inside barrel looks like, and with a proxy collider inside. So a proxy collider consists of a rubber ball and a retractable buckle. And is connected with the wire of the rotatable impactor. So when the impact force is produced, the proxy collider hits around the circle case of the HMD to produce the tangential impact. And we did a pilot study to compare two kind of proxy colliders. One is hard and one is elastic one. And we found that the impact from the elastic proxy collider made of a rubber ball is clearer and more preferred. So, and it's because of the rubber ball deforming increases the impact time. So the rotatable impactor was rotated by a DC motor to provide 2D tangential impact on XY plane. And adjustable support of the rotatable impactor pass through the circle case and attach on the head. And such design prevents the impact from being internal force, so user can easily distinguish the tangential impact direction. So we use two side impactors and rotatable impactors to combine 0.5D normal impact and 2D tangential impact to achieve 2.5D multi-level impact on HMD. So this is how the prototype print look like. And we put the Arduino Mega and also the motor driver and some wires on the back of the head, so yeah, it looks like a pickup crest. So you can see the two side impactor with a Volcker fastener on both sides of the HMD, and also the circle case around the HMD and the rotatable impactor is in front of the HMD. And inside the barrel, we can see the a rubber ball, a proxy collider with a red one is a rubber ball inside. So here is how does it work. So at the beginning, all impactors store the power by extending the elastic band at first. And at the same time, the rotatable impactor is rotated to a target direction. And then when the brake is released, the tangential and normal impact are produced at the same time to provide 2.5D impact. And we can see inside the collider, there's a proxy collider hit around the circle case to provide the tangential impact. So here are a contribution of our paper. We combine normal and tangential impact to provide to firstly realize a 2.5D impact in HMD in VR. And we observe users' impact force perception on their head. So we performed just noticeable difference study, or we call JND study, to observe users' force level distinguishability on the three axes of the head, respectively. And we measure the impact force magnitude for a JND stimuli at first. For the z-axis, we can see the ElastImpact prototype was wear on a mannequin head and affixed on an aluminum extrusion frame. And also, a force sensor was fixed on the bar of the frame, and they are connected by a fishing line. So when the normal impact was produced, the normal impact was measured. And for the SY-axis, the rotatable impactor and the force sensor were both affixed on the frame. And when the proxy collider hits the force sensor, the impact force was measured. And since tangential impact is slightly affected by the gravity of the proxy collider, so we measure the impact force in three directions: sideward, downward, and upward. So here are the relations between the motor revolution numbers and also the impact force in normal impact and also in three directions of the tangential impact. And we decided the upper and lower bounds of this impact in a pilot study. And notably, these two types of impact have different properties, and they are produced and measured in different approaches. So the impact levels of them were examined independently in the JND study. And we can see here there is a sharp force increase in the normal impact, and such sharp force increase is also in the tangential impact. But we can also see here the rubber ball deformation prolongs the impact time, as we mentioned above. And here are the setup of the JND study. To prevent the additional weight of our ElastImpact prototype affecting users' distinguishability, we eliminated it using the pulley system. And in the JND study, each stimuli consists of a base and offset intensity, or here we call force levels. So participants needed to answer whether the stimuli were the same or different. So the base and offset force levels increased exponentially, which complied with the JND standard. And the order of each stimuli were randomized, and each condition was repeated once. So the result of the friction responses the results show the friction of responses that the pair of stimuli were supposed as unequal. And okay, we can see for the normal impact, the distinguishability at level 1.3 and offset level 0.8 is over 90%. Therefore, the three levels 1.3 and 2.1 and 2.9 Newton were chosen as the normal impact. And for the tangential impact, although the distinguishability over 90% are in the several base levels. And however, to provide a more intense impact to enhance VR realism, so we choose the base level as 1.1 Newton and the offset level as 0.8 Newton in both assets. So there are three levels, 1.1, 1.9, and 2.7 Newtons are chosen for the tangential impact. And since the effect of the proxy collider weight, as we mentioned before, is quite slight, so we ignore it and use the sideward impact data for the following. So we performed another VR experience study to verify the performance of such normal and impact combination, and to observe that compared with other methods, whether the impact of ElastImpact enhances VR realism. So there are two VR applications were experienced. The first one is a boxing game. So a virtual boxer threw three kinds of punches to the participant: a quick light jab, and a heavy hook on the side of the head, and also an uppercut on the jaw. So here are the combination of the normal and tangential impact levels. Okay. Yeah. And the other one is a goalkeeping game, and there are five cannons in different positions and in different directions to ejected a different type of ball in different speed respected to the participants. And the combination of the impact are as shown here. So we got the left, down, middle, up, right, five cannons. Okay, so in our study, three first methods were examined and compared, including 1D push, 1D impact, and 2.5D ElastImpact. And all of them were implemented using the ElastImpact prototype. And in 1D push, the HMD pushed users face as in a face push. And in the 1D impact, the tangential impact is disabled, and only the normal impact was provided. So here are the results, and in the comparison between the 1D push and 1D impact, and it shows that producing impact instantly enhances VR experiences in all factors, including realism, distinguishability, enjoyment, and preference. And in the comparison between the 1D impact and 2.5D impact, it verifies that combining a tangential and normal impact enhances VR realism. So here are some limitations and future work about our work. So the current prototype provides normal impact only on one direction in the z-axis, and we envision in the future maybe we can provide the normal impact including s and y-axis as well. And the second one is currently, users is hard to perceive the upward impact, but falsely distinguish as a downward impact. And this is because of the design of HMD with a stripe on the top of the head, but without a stripe on the bottom of the head. So when upward impact happens, the HMD moves up, but user will not really feel that. But after they move down due to the gravity, and they will feel the downward impact. So this is the limitation of the current prototype. And we also hope to lighten and downsize our prototype if it will become like a built-in device in the future HMD. And then the rotatable impactor for now is only within the half resolution in clockwise and counterclockwise. So we hope in the future maybe it can rotate more than one for resolution. So in conclusion, we propose that ElastImpact on HMD provides 2.5D multilevel impact to enhance VR experiences. And we understand that three levels are distinguishable in both normal and tangential impact. And we also verify that 2.5D impact from our ElastImpact are significantly enhances VR realism. So yeah, that's my presentation. Thank you for your attention.
Okay, we have time for a question? I have a question. I was wondering, aside from like boxing and soccer, do you have any other thoughts on what types of experiences, maybe even non-entertainment experiences, might be useful for?
Non-experiment. Wow, I think this work is really for entertaining. So, maybe we'll find some. Yeah, maybe I don't know in the future VR movie or something. It's just like for the 4D movie. Maybe in the future, everyone see a VR movie, they can use it when the scenario is quite provide impact. They can feel it by using this kind of HMD device. Yeah.
Maybe a VR meeting kind of scenario. Maybe like a VR meeting, a video.
Yeah.
All right, let's thank our speaker again.